All right, so that's all I wanted to say as far as sort of where we're at in the course at the moment. More to say maybe next week as we get into the sort of stretch run, the end kind of last few weeks of the course. So for now, we're going to continue talking about neural networks, and we're not going to quite finish the chapter today, but we will do so tomorrow, or a week from today. What we're going to do today is really finish talking about the theory behind neural networks, for at least finish from our perspective. And then on Tuesday, we'll get into how do you train and tune neural networks, and specifically, what are some of the things you do in R, what's the general strategy for tuning them, and so forth. Okay, so to see where we're going today, let's go back to the idea of a basic perceptron. Okay. So we have in the basic perceptron our various inputs. So the bias, and then the various values of the input variables, say x1 through xp, corresponding to the features. And these feed into the net input. And each of them, of course, has associated to it a weight. Say, so the weight for the bias can be written as 1, and then the weights W1 through WP for the various inputs. And then in the basic perceptron, this feeds into an activation function. And the specific activation function we're talking about here is the binary step, where it jumps from 0 to 1, based on whether or not the net input is greater than 0. And then that determines an output, whether a 0 or a 1 in this case. And so for an example of using the basic perceptron setup given here, recall that we can build a logic circuit called a NAND gate. So this is kind of a computer science application of using a perceptron. So we can build a NAND gate using a basic perceptron. All right, so the idea behind a NAND gate is you have two binary inputs, x1 and x2, which take values 1 and 0. And the NAND gate should return a 1 unless both of them are true. In other words, if they're both 1, then it returns a 0. Okay, so just reminder how that works. And we wanted to set it up so that the net input does this. And the way to do this was one way to do this is to use 3 as the bias. And now x1 and x2 will both take the weight -2. Okay. So now what's the output? If we pass this through the binary step, the output is 0 if x1 and x2 are both equal to 1, because then the net input is -1. So 3 minus 2 minus 2 is -1. But otherwise, the output will be 1, because if both of them are 0, the net input is 3. And if one of them is 0 and one of them is 1, the net input is 3 minus 2, 1. So in all cases, except when both x1 and x2 equal 1, this thing will produce a positive output. Okay. All right. So just a kind of a reminder, so it's 1 if and only if x1 and x2 both equal 1. So in other words, are true in the sense of the circuit. So NAND stands for not AND. And that's exactly what it's doing. It's the negation of the AND operation. Okay. So that's all well and good. It's a fairly basic example. But the idea is there's a lot we can build off of this example, surprisingly, despite the fact that it's relatively simple. So we can show the following. Okay. So using these basic perceptrons and linking them together, in other words, forming a neural network. So basic perceptrons can be used to build a neural network, that is equivalent, so in other words, produces the same outputs of zeros and ones to any logical network, any network of logic gates so that's what I mean here is, so when we say any logical network, we mean any system of logic gates. So a logic gate meaning a 0-1 gate that implements some logical operation, such as and, or, negation, etc., all the logic operations. Okay. So you can build any logical network of specifically consisting of NAND gates. So in other words, linking NAND gates together in various ways. Okay. All right, so that might sound very particular, right? That okay, so what? That's just NAND gates. That's the only one we're saying we can build them out of. But there's a really interesting observation from computer science. Any logical function, so aka a logic circuit, so aka any logic circuit, can be constructed from some sequence of NAND gates. So any logic operation you want can be obtained by putting a various sequence of NAND gates together in the right way. Okay. And so the way that that gets described is to say that NAND gates are universal for computation. Oops, straighten this out a bit. So this is a neat observation of computer science, that NAND gates form a sort of universal object. Okay. All right. So what does that tell us? Well, perceptrons are universal for computation. Okay, so that's kind of neat. So any sort of theoretical computer science circuit, any logic circuit, can be constructed using perceptrons because we can implement the NAND gate. Okay. All right, so one of the upshots that we get from that, a nice observation, remember this is just the basic perceptron, where we use the net input and we have the 0-1 activation function, right, the binary step. So even just basic perceptrons are highly general. Okay. There's a lot you can do with them. Okay. But this raises an obvious question. Did we just reinvent the wheel? Right? NAND gates and logic circuits have been around for a long time. So did we just kind of reconstruct something that already exists in a different terminology and different language and different kind of notation, but not get anything new? So that's an obvious question. So, but are they just a new formulation for a NAND gate, for NAND gates? In other words, is that all they are? Is just kind of NAND gates linked together? Okay. Because that wouldn't be very interesting, but thankfully the answer is an emphatic no. Okay. There's a lot more to them. Okay. So the idea is, if they just sat there statically, if we just linked a bunch of these together and didn't at all look at change the weights and the biases, or think about generalizing the activation function, then that might be the case. Okay. But the idea is that what we call learning algorithms and we're going to specifically get to what we mean by this a bit later, can be used to tune the weights and biases. Okay. Of neural networks. You have no such idea of learning for NAND gates. A NAND gate is just a circuit, right? It just inputs zeros and ones in a certain way. Okay, and that's all it does. But with neural networks, we can actually tune the weights and the biases so that the network, in some sense, learns. Okay. So, moreover, this happens automatically. So, in response to what we might call external stimuli. And what we really mean by that, not to make it sound too fancy, such as training data. Okay. So the idea is if we feed the network data and it learns from that data, then it tunes these weights automatically. But what we mean by automatically is it doesn't require a computer programmer to go into the neural network and adjust things manually, right? So when we were talking about basic perceptrons, we said, okay, if we wanted to do such and such, we wanted our perceptron for the wine festival to say we're going to go if it's nice weather and not go if it's not nice weather, and so on, right? And we saw that we could manually set the weights to do that. Well, it would be a real pain if we had to go in and fiddle with the weights ourselves for any neural network where we want to adjust how it's working, right? So these happen automatically in response to external stimuli such as training data, not requiring any manual intervention from a programmer. So all the learning and all the adjusting takes place in the background. The network does this itself, right? So that's the whole point of a machine learning algorithm is we just sit back and let it do its thing. Okay. And we're going to talk in a little bit about how this happens. What's going on in the background of the neural network? Well, a consequence of what's going on, as we'll see, is it makes it hard to interpret, say, what the weights and so on mean. That's okay, right? So, and one way to kind of summarize what we just said is that networks of circuits, right, NAND gates and so on, how kind of a traditional computer logic circuit of zeros and ones have rigid pre-programmed rules. We know exactly how logic gates are supposed to work, and they do their thing. And they do that thing well, but that's all they do. Okay. Neural networks, on the other hand, learn and adapt to solve problems. So they are much more than just some sort of new spin on logic circuits. Okay. Very, very flexible, in some sense, kind of machine learning technique. In fact, and I wish I had time really to prove this, but I don't. But this is something it's interesting to go look up. And well, at least even to prove it, like kind of to wave my hands at the proof. The actual formal proof is difficult. So I'll say in parentheses, almost, because there are some requirements here, any continuous function can be implemented using a deep neural network. Yeah. So, like for instance, you can find a neural network that would describe the sine function or describe the function e to the x, the exponential function, and so on. And in fact, the idea is you can locally approximate it, okay? And that approximation you can make essentially as good as you want if by tuning the network. So this is actually a really interesting kind of mathematical observation. And maybe it's not the most applicable thing, but it's really neat to see that a neural network in some sense is a very powerful mathematical tool, not just a computational tool. So that's just a neat observation. If you it's something worth looking up if you have some time and you want to do some reading. It's an interesting. You'll find some articles about it, I would say, if you search for it. All right. So we've been talking about this idea of a neural network gets to learn automatically and so on, and we're going to get to that pretty soon. Okay. That's called backpropagation. But first, let's also consider neural networks also have flexibility coming from the activation functions, as we talked about last time. So neural networks also gain additional flexibility over, say, circuits over logic circuits, etc. By adjusting the activation functions. So the fact that we have lots of choices for these, and we can choose whatever we think is we want to use in various places. And there's lots of flexibility in terms of making those choices. Okay. So rather than the binary, so what we were describing was for a basic perceptron, and we already saw that there's a lot there. So for instance, let's go back to the question that we talked a little bit about at the end of last class when we talked about activation functions, which is why sigmoid neurons, right? Why replace the binary step or the rectified linear unit with something with a sigmoid neuron? So just recall a sigmoid neuron is the name we often use for a perceptron whose activation function is either the sigmoid function sigma of x equals 1 over 1 plus e to the negative x, or the sigmoid linear unit. Which we sometimes abbreviated SILU, and this was x sigma of x, so x over 1 plus e to the negative x. Okay. And what we saw is that the sigmoid function provides us something along the lines of a smoothed out binary step, and the sigmoid linear unit provides something along the lines of a smoothed out rectified linear unit. Okay, so then when I say why sigmoid neurons, so why replace the binary step with an activation function that's, well, and there's progressively more and more we can kind of add to it. So continuous is at least what we might want. So that's like RELU. differentiable, okay, or even we might call smooth, or what sometimes the term sometimes described as C infinity, or infinitely differentiable. Okay. And in fact, sigma of x and SILU satisfy that condition. So they're not only differentiable, but they're infinitely differentiable. You can continuously take derivatives, and every derivative itself is continuous and differentiable. Okay. So you have a nice smoothness structure there. Okay. So what we're going to do is kind of work through a kind of a fake example here, but describing the general process of why this is important. Okay. So learning algorithms tune. Okay, so what does it mean to be tune the weights? Well, change them, adjust them, right? Weights are numbers. They're numerical quantities. So essentially, we can treat them like hyperparameters and tune them, right? We can look at different values of them. And so forth. Okay. So the learning algorithms tune the weights and bias. As the neural network learns. Learns here means gets trained on the training data and assesses its performance and so forth. We'll talk about how to do that in a minute. Okay. So what we saw towards the end of, or at the end of our last class, where we were talking about activation functions, is a desirable property is small changes in the weights lead to small changes in the output. And last time we saw that because of the sigmoid function being differentiable, you can actually you can find a bound on this. Basically, it's controlled by some linear multiple, some constant multiple of the derivative. So it's got a kind of a linear growth, which means you've got a lot of control over what's going on. Okay. The problem with a basic binary step is that may not happen. Okay. So with a basic perceptron, by which I mean binary step activation, small changes in the weights could, they don't have to, but could lead to big changes, big here in quotes, in the output. Okay. Yeah, I mean, you might say, well, changing a 1 to a 0 or 0 to 1 is not big, but of course, in the context of a binary step, on, off, it is, right? You're changing, there's only two outcomes, and you're changing from one to the other. So a 1 to a 0 or a 0 to 1. That, in the context of binary step, is a big change. Okay. So the idea is, what we wouldn't want is like the weights just to sort of change a tiny bit and then suddenly flips a switch from on to off. Right? That's not necessarily desirable to have it work that way, have it operate in that fashion. Okay. All right. So let's work through a fake, kind of like I said, it's sort of a fake example. Okay, I mean it's a real example, but what I'm going to describe, I mean, you may not. It's sort of just a hypothetical. Okay, so let's go back to the digit recognition question, right? The MNIST problem. Okay. Okay. So suppose we've trained a deep neural network on MNIST, on the MNIST data. Okay. So this is where I'm saying it's a hypothetical. Okay, we're pretending we've trained a deep neural network on this data, and it's frequently misclassifying ones as sets. Okay, so it's having a hard time distinguishing between a 1 and a 7. It's not picking up kind of the length of the upper bar or whatever you want, however you want to describe it. Okay, so we try to fix this by tweaking the weights. In other words, tuning it more. In the various perceptrons, so the various perceptron nodes. Until the deep neural network is handling this problem more accurately. Okay, so that would kind of, that's what we want. All right, so we kind of want to almost manually fix that problem. Okay. So now so the idea is that if small tunings are happening on the weights, so if the activation functions in the neural network, the deep neural network, are sigmoidal, or SILU, or at least continuous, like RELU, the rectified linear unit, right? So at least if we have continuity, okay, so if that's the case, this should work, right? Again, there's no guarantee, but the idea is that small tweaking of the weights maybe can fix that misclassification problem without breaking anything else. I mean, that's kind of the key idea here. We don't want it to somehow completely mess up what's going on. Okay. But if the activation is binary, if the activations are binary, because there's more than one here probably, somewhere in the network, a perceptron may flip in some sense. It may flip from 0 to 1 or 1 to 0, right? So it just changes the output off some tweaking, okay? But here's the whole point. That flip then propagates through the rest of the network. It's sending it used to be sending a 0, now it's sending a 1 to the next set of nodes, or vice versa, right? This can change the entire network in complicated ways, because of course now lots of things can change. Okay, because now that change sort of passes downstream into the network, and it can affect all kinds of other changes elsewhere. Okay, so maybe now, so here's kind of the hypothetical, right? So maybe Now, 1s and 7s are being classified more correctly. But now the neural network is mixing up 4s and 9s. Maybe. Who knows? That's just an example. Maybe it's accidentally now thinking that the 4s are just uncompleted 9s, right? Something like that. Or maybe it thinks the 9s are 4s where they're just it's the 4 with kind of a closed top, and it's just not sharp enough. Okay. So replacing binary step activations with something that has more continuity, including smoothness if we want it, can, well, fix this sort of problem. Okay. So anytime we replace something simple with something more complicated, it's worth asking why we're doing it. And that's the idea here, is by doing it here, by replacing the very simple but kind of not very subtle activation function, the binary step, by something continuous, then we can allow small changes in the nodes, in the weights, to affect only small changes throughout the network, hopefully, in the outputs from each node to the next. Okay. And presumably then this can be controlled. Now, the issue with just pure continuity versus smoothness, like the sigmoid neuron example, so sigmoid linear unit, sigmoid function. Okay. Smoothness is desirable to have control over, in some sense, how big the changes are. So in other words, we're saying kind of in a generic way that small changes in the weight should lead to small changes in the outputs. But the word small, obviously, there is not being formally defined. The idea is, can we control this in some kind of way where we can actually say, give a growth order on the error, for instance, and so on. Okay. And usually you need some kind of differentiability condition for that. So you can basically say how quickly things are changing. If you have like a sharp corner point, well, then the gradient at that point doesn't have to exist. And so the change can kind of be infinite in some sense. You can't control the size of it. Okay. And this is important because the neural network learns using derivatives, specifically gradients. Okay. And so with that in mind, I've kind of alluded to this was coming. We've talked about learning algorithms and how the neural network learns. This has a name. It's called backpropagation. Okay. So backpropagation is how a deep neural network learns. In some sense, it's the way the network trains itself on data, on training data. Okay, so we'll often use the term forward pass. And what this means is just a run through a deep neural network. Okay, and what do I mean by a run through it? Well, so the idea is we input information into the network, the information passes through. Okay. So inputs So inputs are fed into the deep neural network. Okay. Information, so in other words, output information from each node to the next, passing through activation functions. So propagates forward through the layers to ultimately generate an output. Hence the name feed forward, right? Remember, we're talking about feed forward neural networks. Information is only flowing in the forward direction through the network. That's what we're talking about here. So we don't have a more complicated network like the ones we talked about, feedback neural networks or recurrent neural networks. Okay, so the idea is the network is going to pass data through itself and to the end, and then generate an output. So let's describe what happens on the first forward pass through the network. Okay, so what happens? The very first time you initialize the deep neural network and feed it data. Okay. Okay. So the deep neural network goes through the following sequence of operations. Okay. Number one, it selects a batch of observations. Doesn't have to be all of them, as we'll see. So you don't need to feed it the entire training set all at once. It will simply pick a subset of that if you wanted to, and this is all sort of tunable. All these are all hyperparameters as usual. You can decide how this is going to happen. The next thing is kind of interesting. So for the very first forward pass, the network itself has no inclination how anything should be weighted. Okay? So what does it do? Well, it randomly assigns them. So it randomly assigns weights. Across all the connections. So everywhere there's a node connection, it simply it puts a weight there. It just assigns a number to that connection. Number three, it predicts an output. So it passes the information through the system. And then it tries to assess its own performance. It measures performance. How well did it do prediction-wise via some loss function or functions. Okay. So you're going to have some way for it to evaluate how well it did, right? So if you did this, say, with the Ames housing example, the first run through the neural network is going to make some predictions about houses, housing prices, selling prices of the houses. And then it's going to look at, okay, well, how far off was that, right? You're going to use sum of squares error, mean root square error, and then, and there you go. Okay. Now, you're probably not going to get a great prediction off that first forward pass because all you did is randomly assign the weights, right? The network kind of just almost essentially created a random output. So what it needs to be able to do then is go back through and figure out where it was making errors, like what nodes were contributing to the loss function, and then how to make that better. How can you change the weights to reduce that? And that is what's called backpropagation. It's what happens after this first forward pass. So backpropagation is how the deep neural network assesses its own accuracy. So it kind of self-evaluates. And auto-adjusts the weights. Auto-adjust meaning it does this itself. You're not going back through and adjusting them by hand or anything like that. So it auto-adjusts the weights to improve its performance. And this is what we mean when we say it learns. Okay. It learns by seeing where it's making mistakes and trying to fix those mistakes by adjusting the weights. Okay. So after step 4, the deep neural network successively performs what we call mini batch SGD. Okay. And what SGD stands for is stochastic gradient descent. So I think I mentioned when we talked about stochastic gradient descent that it was going to come back. It wasn't just for gradient boosting in chapter 12, but it would show up for neural networks as well. And this is where it does. Okay. And what does mini batch SGD mean? So now what it starts to do is it starts at the output that it has and assesses it by some loss function. And now it starts to go backwards through the network. Okay. So it starts to try to fix its mistakes as much as possible from the last one, from the outside in, so to speak. So working backwards through the layers. The deep neural network does the following. Okay. So step 5. So kind of this is the step process. So at step 4, we've made our first pass through the network. Now what happens after that? Step 5. It computes the gradient at each node with respect to the weights. In other words, it treats the weights as the different variables. Oh, come on. Okay. It adjusts the weights in the direction opposite the gradient So it looks for the gradient, essentially looks for the largest, the biggest change, and then goes in the opposite direction. So the biggest negative direction. Step 7, let me make that look a little nicer. It chooses a new batch of observations. Okay, so it's worked backwards through all the layers, adjusting the weights as it goes based on the gradient. Essentially trying to get the biggest decrease in the loss function, the greatest change in the negative direction. Okay. Chooses a new batch, not batches, new batch of observations. Okay. It then repeats a forward pass on these observations. It repeats after that forward pass steps 1 through 7, or 4, sorry, through 7. So it predicts an output, assesses the output by a loss function, works back through the network, computing the gradient of the weights at each node and adjusting in the negative direction to decrease the loss function. And so it goes through all those steps and then continues essentially steps 4 through 9 until the loss function is minimized. So it keeps trying to reduce its error by tweaking the weights until we reach some minimum for the loss function. Okay, so that's what's going on in the background of a neural network, and it's doing all of this without having essentially to be supervised. You don't supervise in the sense of you don't need to be looking at what's happening. You're supervising it in the sense that it's a supervised learning algorithm. It's using target data to assess its performance. Okay? But so all this is going on. As a result, the weights that you end up with they're not necessarily really interpretable. Okay? So like the weights in the network all are kind of related to each other in very complicated ways. They're like about just the opposite of, say, like the coefficients in a linear regression where you can interpret them nicely. The weights really are probably going to be almost meaningless, like as individual numbers. But the result is the network itself it can be very accurate. It can make very good predictions. Okay. Now, there are aspects to the mini batch SGD algorithm used, so that you can tune. Okay. So the specific variation of the mini batch SGD algorithm used is called the optimizer for the deep neural network. So this, as it turns out, is a tunable hyperparameter of the deep neural network. That depends on, among other things, the learning rate. Okay, so learning rate is going to be just like it was a hyperparameter for gradient boosting. It's going to be a hyperparameter for deep neural networks, and we're going to talk a week from today, next Tuesday, on what are some of the hyperparameters of deep neural networks and how are they tuned. Okay, but the standard default for mini batch stochastic gradient descent SGD is called RMS prop and works sufficiently well for many applications. So you often don't have to actually adjust the algorithm itself. You just tune things like the learning rate. Give me 1 second. I think I'm missing a page. Double check. No? Okay. Actually, okay. No. There's just one more thing to say. So at its core, the backpropagation algorithm consists of two things. Okay. It consists of, number one, the choice of optimizer. So in other words, what stochastic mini-batch gradient descent algorithm is being used. And number two, the choice or choices of loss functions, loss function or functions, depending on one or more. Okay, so that's ultimately what backpropagation is. It's the process described, but the two things that change how it works are the choice of the gradient descent algorithm, the mini-batch stochastic gradient descent, and the choice of the loss functions used to assess performance. Okay, but that fundamentally then is the learning process of a deep neural network. Okay, so that's where I wanted to stop for today. And as mentioned, in a week, we're going to talk about the various hyperparameters and how to tune the network and how hyperparameters affect performance of the deep neural network. Among other things, we'll see that tuning deep neural networks requires a lot of computational power. The sort of growth in runtime can be quite prohibitive when tuning them. So all that coming up a week from today. Enjoy your long weekend.